All right. Are my windows open properly here? I think so. Yeah, we're going to go with yeah. Oops. This thing. I hope you had a decent weekend. Um, yeah, let's see. 70 seconds. Okay, this may be a good time. I should say in my calculus sections, it's 175, and I am trying a new experiment, or rather, I have from the beginning of the semester. I use slides for them, and right before class starts, I just have a quote up, and I changed the quote last week or over the weekend just due to some recent events. So you get better than a quote. You get the. I do not really play guitar, but you get the song, right? Lean on me when you're not strong. I'll be your friend. I'll help you carry on. For it won't be long till I'm gonna need somebody to lean on. All right, that was fun. 15 seconds. Yeah, why not? If you are a Wisconsin resident, I just want to remind you that there is an election tomorrow, so please make your voice heard. And then the census. So I signed into Canvas this morning and saw that that if you live off, or sorry, before spring break, if you lived off campus, you've got to do the census yourself. If you were living on campus, the campus itself is doing something to help submit some census data on your behalf. I bet some more information is coming, and if I find out more, I will let you know, because the census is very important. It's important for, to make sure that the right representation of students was all there, because, resources at the state and federal level coming into this area also matter. Think about future students and that kind of thing. Okay, let me move this window here. Oh, some announcements, I guess, would be good to start. Actually, let me move my timer to the next screen. I'm gonna drag that over. Okay, there we go. Quick announcements, you'll see them in the corner of PDF that starts S31 if you look yourself. But today's Monday. Please turn in that exam by the end of the day today. I'll just write this as well, make sure we've got it. If you're just joining, you missed the song, but that's okay. You can listen to the recording later once I upload it. There's a quiz due. So the quiz is dated for Tuesday, but again, just due to recognizing schedules are all so strange, I'm just trying to give some extra time to work on these things. So while the quiz will be available on Tuesday, you can complete it anytime between Tuesday and Wednesday, so turn it in by the end of the day Wednesday. As is typical, there's a response due every Wednesday. I had not posted this until realizing I got an email on Friday about this, so I not only made the response that's due this Wednesday, I actually just went ahead and made the responses due for the rest of the semester, so won't run into that trouble again. Homework. There's a homework due this Thursday, as there is every Thursday. Once you're done with the exam, maybe you already are and have turned it in, but once you're done, just please get started on the homework ASAP. Oh, one comment about the quiz I forgot to mention is that there was some kind of format related things. I had a number of people actually struggling with submitting things. So I thought, why not we just do this? Since you're all used to turning in homework on Gradescope, I'd like to just have the quizzes turned in on Gradescope as well. So create a PDF, and for the quizzes, whether you want to tech that up and then make the PDF, or you just want to write it out and take a picture and then use a free phone app to create a PDF, one way or another, I think just for the upload mechanism, Canvas does seem to have some strange features to it. So let's just use Gradescope if that works out for y'all. Okay, I think that's it for announcements, but I will pause for about 20 seconds, see if anybody unmutes a mic and has any other questions or things I can clarify. And again, if you're just joining us late, the main one is exam. Please turn it in by the end of the day and then get started on homework right away. Okay, not seeing anybody unmute. We are starting section 4.8. So this is the section on functions. What do I need to say about this is not what you think functions are, or you have some ideas of what functions are. And I guess what I'm going to ask you to do is let's borrow some of that terminology, and at the same time, I guess, and I recognize this, it's not your fault, but the way you think of functions comes into conflict with the way that I think about functions. And in a sense, you've got some baggage related to this, and I want you to try to let go, right? So it's like everything you know about functions, try to ignore it for a moment, and it'll all fit into the story. But I think the thing is that your experience in calculus sort of accidentally maybe trains you to think about functions a certain way. I think it's extremely important in this section to do the reading. So please get the PDF online. If you don't have the physical copy of the handbook with you, please take a look at section 4.8. This is part 1 out of 6. We're going to spend a lot of time in this section because I recognize that this section tends to be a little challenging for folks, but if you really pay attention to the things that we've done so far and keep the habits, I think this will go actually quite okay. Let's see. First, the only recall that we'll do, and then we'll just dive into it, is please recall that a relation from a set A to a set B. So I'm not even writing all that down. It's not as formal. I'm just trying to help you remember. This is a subset of A Cartesian B. Okay, here's the definition. Let me scroll down a little bit, actually. Okay, definition. So this is a definition, so we will be a little more formal than the recall that we just had. But let A and B be sets. Okay, you got to start with 2 sets. Okay, so whenever you have these setup-like sentences, you got to make sure that that's stuff you already have established before. And now the new thing, a function, I'll underline the new word, from A to B. We've already seen the language from A to B. We saw it back here with relation from A to B, so not too surprising so far. Okay, this is a binary relation from A to B. Satisfying 2 additional properties. So let me just number them 1 and 2. Property 1, for all A in capital A, there exists B in capital B such that ordered pair AB belongs to F. Oops, I forgot that up here. I'm going to just shift over this a little bit. I wanted the notation here. I forgot about that. This is what I get for trying to do this from memory and I look at my notes. Part 2, so the function we're going to name little f here. Okay, and then so part 2 is for all A in A, for all B in capital B and for all little c in capital B, if the ordered pair A, B belongs to F and the ordered pair, let me move that a little bit, it's too close, and the ordered pair AC belongs to F, then B is equal to C. Okay, that in a sense completely defines function, but like back when we learned implication, we had like additional words like hypothesis, conclusion. So same sort of deal here. This is a good place to include one other piece of information. So one last sentence to complete the definition. The set A is called the domain, and B is the codomain. So let's say with this one added sentence, let me box it. This thing is just all that important. There's our definition of function. Okay. So I'm sure there's a number of questions that you have. One might be, what about range? Range, you might say, did you mean to, instead of saying domain and this funky word codomain, did you mean to say domain and range? I meant the word codomain in the official definition. This word range is sort of related to codomain, and exactly how, we're going to discuss this a little later. So already, if you're like, this codomain, that's not a word. It is for us, and this is already maybe where you might see that you're running into like the way you think of functions in the past and the way I want you to now view functions are probably, there's already a little bit of a clash there. What kind of a thing is a function? Is it a noun? Is it an adjective? Is it a verb? We should discuss that first. What kind of thingy is a function? So I hope from looking at how the definition is written, we'll say that a function is a noun. Hope no complaints with that. And whenever you have a noun, you ought to always ask yourself what kind of noun, what specific type of creature do we have? And you'll read in the definition. Let me underline this in maybe green over here. But a function is a relation. A function is a special kind of relation, right? It's a relation that satisfies additional properties. And please remember that a relation is a set. So I think the thing to say here is that in addition to having a noun, a function, oh, come on, there we go. A function is a special kind of relation. So just from reading the definition, what I'm trying to say is all functions are relations, but not all relations are functions. And then in addition, if we step back, and we could have said this maybe even right before spring break, is a relation is a special kind of set. Right? Because remember that a relation is defined as a subset of a Cartesian product. So a function is really a special kind of relation. So not all relations are functions, and a relation is a special kind of set. Not all sets are relations. So in turn, we then end up seeing that a function is actually a very, very special kind of set. So I remember even reading back in one of the first responses when people had to react to, wait, everything's either a proposition or a set. Well, what about functions? Well, functions are actually sets, just very special in how they are formatted. I need to make, so you'll see that, I guess to summarize what we have here, it's fair to say that a function from A to B, just to summarize, I mean the official definition is boxed up there, but a function from A to B is a subset of a Cartesian product B which satisfies these two other properties that were numbered 1 and 2, satisfying 1 and 2 from up there. Okay. Just a couple notes. The first note, I'm looking at my notes. This is a comment if you've done any computer programming. If not, you can kind of ignore this, but I just need to state this for the programmers in the audience, is that the concept of function in computer programming is different. It's not quite the same. There's definitely a lot of similarities. I'm not trying to say the CS way is wrong. I'm not trying to say the math way is right. I'm just saying in Math 225, when using the word function, I mean it the way we just defined it. I also do a little bit of computer programming, and I definitely, when I'm doing programming, I got to think about the word function differently, and that's okay. And then I will also make the following comment, and this comment's for everyone. Functions as they are learned in previous math classes. So I'm thinking about, like, when you take algebra and pre-calc, calc 1, 2, 3, those sorts of courses. And linear, I have it in my list, so I'm going to include it. Linear algebra as well. And it depends on kind of how much you dug into this in your linear algebra class. If you took linear algebra, and if you haven't, don't even worry about it. But I should comment that the way that we are going to look at functions right now, we're going to hear the real story. Everything else you've heard is, I don't want to say it's not the truth, but it's like probably a half truth, or like partial, 1/3 the truth or something. We're going to hear the whole thing right now. The other ways you've learned functions in the past fit into the general framework that we are discussing today. Okay. Just a word on notation first, because I think right now the way that things are described seem a little bizarre. And so good chance to review. I'd like to remind you that if capital R is a relation, recall that it was just convenient notation. We could write ordered pair AB belongs to the relation, and this was just shorthand notation for, the shorthand notation for this was we wrote the relation symbol in between the A and the B, right? And we were thinking about symbols like less than or divides as the reason to do a thing like this. Well, because a function is a relation, we could use this notation as well. But for functions, there is a more typical alternate notation. So just like, this relation notation over here seems strange at first. I hope what you're about to see here helps clarify. If little f is a function. Oh, I should pause and just say, remember, a function is, in the end, a special kind of set. So we're using a lowercase letter to describe the name of this function or of this set. And that's okay. Like, even way in the past, we could have used a lowercase letter for a set. So we just generally haven't, because sets we think of as containing things. So we tend to use big letters, but we don't have to. So, all right. So if f is a function, then whenever you have the ordered pair AB belongs to the function, belongs to little f, we're going to use this new, you can always write it like that, but with the notation that we will use, this will look a little more familiar to you, right? F of A equals B. So if you have the ordered pair, first coordinate is the input, and then the second coordinate B is the output. So I hope that makes a little more sense. And just in terms of, I'm trying to connect a little bit, let me box this. I'm trying to connect to kind of the way you think of functions in the past. What I'd like to do, I wish I had a board. I would just point to what we have and not erase it, but I'm going to actually copy and then paste this at the start of my next page here, just so that you have it as a reference. So we'll call this our official definition, but based on the notation thing that we just said, so just a reminder, if you had x, y ordered pair in f, then this becomes f of x is equal to y. So let me box those two things. You can always switch back and forth, either format. Ordered pair belongs to f, or f of x equals y. You can switch either way, just whatever's convenient. It's notation, just like ln is natural logarithm, log base e is just notation. So I'm going to pause, and I'd like you to please write down properties 1 and 2 over here that I just put an arrow at. I'll write them down here in a moment, but I'd like you to write properties 1 and 2, switching from this notation to the kind of more usual function notation that you're used to. And then we'll talk about it in a moment. Give more time. I'll give a little more time. Y'all know why I sang the song that I sang at the beginning, right? Just because the artist had passed away for that song, right? Okay. Right. Okay, so let's write these down. So first of all, the quantifier doesn't change, and that is an important detail. I mean, if the quantifier wasn't important, why have it? So for all a and a, there exists b and b. So for each thing in the domain, there exists a thing in the codomain called b, such that f of a is equal to b. And the second property, just copy the quantifiers for all a and a, for all b in codomain, for all c in codomain capital B. If, and then here's the part where we're going to change up how it's written, if f of a equals b and f of a is equal to c, then b is equal to c. So I hope that looks all right. And now what I want to do is, I think in the new way that properties 1 and 2 are written, now either way is going to be considered correct for us. I just, the original in this big box over here, writing it like in this ordered pair notation is helpful to like really connect that a relation is that a function is a special kind of relation. In fact, I got to say, when I was first studying this material, it was seeing the function as being a special kind of relation that really, I know it's a little confusing at first, but when you actually dig into it and like force yourself to understand it, you go, oh, that's what a function really is, and it really clarifies a lot of things. So with the properties 1 and 2 rewritten this way, I think it's helpful if we interpret what these things mean. So take a look at property 1. It's saying for each, let me use a new color here, for each thingy in the domain, there exists a thingy in the codomain. Think of the codomain kind of like the range. It's not perfect, but like the codomain is where the outputs are from. Right? And the idea is that you get f of a is equal to b. What this is really trying to dig at is that each element, I'm trying to be a little informal right now, so I didn't even say which set, but each element, little a, you know where little a comes from. It comes from capital A. So each little a in the domain has an output. And I'm using this word output even though I haven't properly defined it, but I know that, I want you to use your intuition here for what happens in functions. Has an output, which we're calling b, in the codomain. So I want to have this relate to what you think about functions in the past. Like in the past, I'm just going to write down an example I'm making up on the spot, like f of x equals 1 over x minus 3. Now this doesn't count as a function in our class. I mean, it's not considered clear enough, and I will say something about that in a moment, but like, when I teach college algebra, I write this down and I cross my fingers behind my back and say this is a function to the class. I'm not telling them the whole truth because it's not a good idea to tell the whole truth about it. And I ask that class, I say, hey, what's the domain? And I hope that, some brave soul answers and says, all reals except 3. But if all real numbers except 3 is the domain, that means you ought to be able to pick any number other than 3 and plug it in for x. And you should get a y value. You should get an output. And that's what That's what this up here is trying to address. That every time you have something in the domain, you plug it in, to F, and then you should get an output. The second property, the property up here that has a triple for all, so you've got each time you have something in the domain, and if you have something in the codomain called B, and you have something in the codomain called C, then if the output for A is B and the output for A is C, it's because B and C were not actually different, but they were equal. So part 2 is trying to talk about a function is a, dare I use the word consistent rule. I think a lot of books prior to 225 just say a function is a rule, and I've always been confused by the phrasing. It just is a rule. What do you mean a rule? Rules could be random, but I think they mean a consistent rule. So in other words, what's going on here is so the idea here is B is an output. I won't say the output yet. If B is an output of A, so when A is input, you get B as output, and C is an output of A, these two things imply, they cause this situation where B has to equal C. That's what the second part of function is getting at. We clear what this second thing is kind of trying to get you to do? I mean, there's actually wording that you might have learned from a prior math class. I just pause and see if somebody wants to discuss it. Where has this language appeared?
I just have a quick question.
Yeah, sure.
Where you say B is an output of A, do you just mean the element A, or do you mean the set A?
Oh, good question. Yeah, I do mean, yeah. So I hope everybody heard the question. The question was, when I wrote here, B is an output of A, and I am being a little, in any case, I'm being, what's the word? Informal, right? This is not like with all the quantifiers and all that business here, but this is a lowercase a, where the arrow I just pointed. So little a is supposed to be an element of capital A.
Okay, thank you.
Yeah. So this is just, this in words, what's underlined here in black is meant to try to say the same as what I just circled, this f of a equals b. I'm just trying to, sometimes doing it in words instead of in symbols makes it a little more kind of everyday-ish, but even if it's I don't mean to be, I mean, you lose a little detail, but sometimes intentionally losing some detail might make things clear for the moment. That's all. But let's in any case talk about what this second property is trying to get at. So what's going on here? If there's this input called A, and it's the input called A both here and there. The input is A, and if B is an output, when A is the input, and C is an output, then B equals C. This is trying to address a thingy that you've heard about, I'm sure, in previous math classes, way back to an algebra class. It's phrased a little funny, but it's the phrasing that works for, it fits into the grammar of what we've been looking at. So to phrase this a little differently, this is that one input can't produce two different outputs. So if you have what you believe is an output of A, let's call it B, and so you have, let's call it C, another output of A, it's because B has to equal C. So there's no two different outputs. The language that you may have heard for this, not may have heard, you must have heard this, vertical line test. Right, so that's the language that gets used in like an algebra class to say at a specific x value, you can't have two different y values in the graph. All right, I'll pause, see if we're doing okay overall.
So are these conditions essentially the existence and uniqueness?
Yeah, that's a neat way to put it. I was not planning on phrasing it that way. That's great language that comes from somebody with some like linear algebra-like experience. But yeah, so let's say that property. Let me scroll back actually to do this. You could say property 1, whether you want to deal with it the way it's written up here or the way it's written there. You look at either red arrow. It's saying that for each thingy in the domain, there must exist an output. That's what part 1 is trying to talk about. And then part 2 is trying to talk about, okay, not only is there an output, but that output should be unique. So for each input, you have to get a unique output. Every time you have an input, you get one and only one output. And all the while, the whole point here is the order. You learned a long time ago that you can't switch a for all and other exists in this class, or in math, actually, in general. So you'll see, especially in property 1, because you've got the for all first and the there exists next. I think parts 1 and 2 interpreted properly, not swapping quantifiers when they can't be swapped, gives you like the honest idea of what's going on with a function. Every time you have an input, you have only one output. Can the same output appear for different inputs? That's totally fine, right? Think about like when you graph y equals x squared. The output 9 is used both by input 3 and negative 3. That's totally fine, right? But each input can only have one output. Thanks for that great comment about existence and uniqueness. Another thing I want to point out is in the definition, it starts with the phrase let A and B be sets. And therefore, I know this seems a little picky, but you'll see as the weeks go on why this is going to be super important. So let me write down this warning, because I think this is the trap sometimes people fall in, is please do not only think of, and I'm trying to make an example here, f of x equals like x squared plus sine of x as a function. Okay, sometimes what happens is people think that a function has to have a formula, and I'm using this word very loosely. What I mean by formula, what I just boxed in green right there. Yeah, if you've got a thing like that, this is gonna probably usually describe a function, but not all functions look like this. I guess that's the point, right? So if you see f of x equals, cool, but there's gonna be functions that don't look like that. So I need to, that's the baggage that comes, is I need to get it out of your head that a function has to look like this. A function, just, again, is just how we do things in Math 225 and technically in all math after, is officially a function is a subset of A Cartesian product B satisfying properties 1 and 2. From up there, whether they're written in the ordered pair format or in the more usual function notation. So I can't stress enough that you've got to drop some of your own ideas of what function was from the past. We're going to see some examples in a moment. I actually, related to this, I'm going to make one other comment right now. Because I remember last semester and the semester before, I had somebody usually ask about this on the second or third or fourth day we were talking about functions. So I've been told to not answer a question that people don't ask, but I think right now I'm going to make an exception. I want you to get this out of your mind, and I don't want you to be confused about the examples we look at. So I'm gonna make this comment right now. Also, don't think function equals continuous function. Try to get that out of your mind. Back in Calc 1, a continuous function was like, at least informally, was a function you drew without lifting your pen. There was an official definition of what continuous function was that was usually presented in 3 parts, and it dealt with a limit and all this stuff. We're not going to dig into that right now. That's for a later math class after 225 to like really dig into it. But for now, I think let's use good habits. A continuous function, look, the adjective continuous, right? It's a special kind of function. So not all functions are continuous functions. There are continuous functions, and then there are other functions. Continuous functions in their official definition. If you look up an official definition of continuous in a calculus book, there's going to be some limits involved. So I want to get out of your head the idea that a function is only those things that you can draw without lifting your pen. Okay, a function officially is just whatever fits our definition. To really try to break that in, I think all the rest of class today is just example after example. And I'm going to really, I want you to look carefully at these examples. I have different examples in the handbook, but I need to get out of your head that this, what's in the green box still, that a function has to be given by a formula. I need to get out of your head that a function has to be able to be drawn without lifting your pen. That's a continuous function. So here's our first example to try to really break some of those habits right now. So I've got the set capital A is 2, 3, 4, and the set B is the set 3, 6. So cardinality of A is 3, cardinality of B is 2, and then I'm going to define for you a set called lowercase f. This set F has the ordered pair 2, 6, has the ordered pair 3, 6, and also has the ordered pair 4, 3. So since, as I defined it, since F is a subset of A Cartesian product B, right? Remember, A Cartesian B is the set of all possible ordered pairs. A Cartesian B would have had 6 ordered pairs. But since we've got this subset, and F satisfies properties 1 and 2 from the definition. Remember, property 1 is every input has an output. That's the existence part. Property 2 was every input in the domain has only one output, not multiple outputs. So F is a function. So F is a function with domain capital A and codomain capital B. There's our first full-on example of a function. Want to just pause, see are we okay with that? See if we've got any questions. We're technically done with this example, but I just to say one other thing about it. Notice just using the other notation, since we've got the ordered pair 2, 6 in F, we can also write F of 2 is equal to 6. And same thing with the next ordered pair, 3, 6. We can write that in the more kind of usual notation. F of 3 is equal to 6. So you'll notice that both input 2 and input 3 share the same output 6. That's okay. There's nothing, that's fine. That's okay. Nothing about the definition of function prevents that from happening. Time for example number 2. I will pause though. Okay. Time for example 2. New example. So let capital A, I'm using a new capital A. So, oh no, yeah, no I'm not. 2, 3, 4. I am using a new set capital B though. So for capital B in this example, I'm using the set 7, 8. Okay, and then since we used lowercase f up there, I'll just use a G. I mean, G has the ordered pair 2, 8 as an element, has the ordered pair 3, 8 as an element, and has the ordered pair 4, 8 as an element. Okay, so since G is a subset of A Cartesian B, satisfying properties 1 and 2 from the definition, G is a function from A to B. Maybe you notice something strange about this function that you want to talk about?
It's a horizontal line.
Yeah, it's a well, yeah, okay. It's a horizontal line in some sense. I appreciate the comment. It's actually not even the entire horizontal line, is it? I don't know if you can see in my camera view right now, but I'm just sort of gesturing and creating a horizontal line with my hand, and this is not like the traditional algebra or calculus function g of x is equal to 8. It's not, I don't mean that constant function. In some sense it is, but it's actually just 3 dots, right? It's 3 dots on that horizontal line. I mean, that line has an infinite number of points on it. We just literally only have 3 dots when the x-coordinate is 2, when the x-coordinate is 3, and the x-coordinate is 4. So do you see that, like, if it's just literally 3 points in the Cartesian plane, we can't really talk about continuous, right? Because you can't connect those 3 dots. Those 3 dots, to draw them, you have to lift your pen. So we got to get continuous out of our mind. But I appreciate that comment. The other thing I want you to notice is, I know that you see that 7 is an element of capital B, but 7 was never an output. You'll notice that the way that all 3 ordered pairs are written, the second coordinate is always 8. So notice that 7 was never used as an output. And that's okay. So even though 7 is an element of the codomain, 7 never was used as an output, and there's nothing about the definition of function that says that everything in the codomain has to be used as an output. So if it's not part of the official definition, then we don't need to check for that in order to have a function. So the comment I'll make is that not every we're done with that example, but what I want you to gather from this example is not every element of the codomain must be an output. You will note sort of the converse of this needs to be true. Everything that's an output has to be an element of the codomain. That's what property 1 of this definition of a function is about. Okay, hope we're doing okay overall. Let's look at a non-example. I showed you 2 examples. Neither of them is continuous. Neither of them should be really thought of as having like a standard formula like what we boxed in green. Let's see. It's good to look at non-examples too. So I've got the set A, which is 3, 4. The set B, which is 7, 8. So both A and B have cardinality 2. I'd like to define let H equal the set with ordered pair 3, 7 and ordered pair 4, 6. Okay, so then H is not a subset of A Cartesian B. No, H subset of A Cartesian B, that doesn't happen, so I put a slash through the subset symbol here. And this is because, take a look in that second ordered pair, the second coordinate is 6, and 6 is not an element of B. So the point is, so H is not a function, or let me clarify, at least not, H is not a function as long as, well, if the codomain is this set 7, 8. You could tweak this. It's currently a non-example. You could tweak it into an example. All you got to do is change up B, have either replace the 8 here with a 6, or just make B have an additional element. You know, B could be 6, 7, 8. But as currently written, you don't have a function from A to B. B cannot, the current B here of just 7 and 8 cannot be the codomain, because you've got the second coordinate being a 6. Here's another non-example. Oh, I should pause. Sorry, I should keep in mind there's always like a 5-second delay from when I talk to when you hear it. Okay, here's another non-example. Let capital A be the set 3, 4. let's have B the set 6, 7, 8. Let H be the set with the ordered pair 3, 7, and that's it. What's the problem here? What's the deal? You'll notice H subset of A Cartesian B. Yeah, that happens, right? So the ordered pair 3, 7 is one of the ordered pairs in A Cartesian B, but property 1 fails. Remember, property 1 was every input needs an output, and here as written, 4 doesn't have an output. As another non-example, let A equal the set 3, 4. Let B equal the set 6, 7, 8. Sorry if this is all a little dry, but like this is kind of, I'm trying to model here what you should be always doing with functions. With just any definition is that you should like pick it apart, like one detail at a time, to see what makes something an example and what makes something not an example of a definition. So I'm going to look at H as the set with ordered pair 3, 7, the ordered pair 3, 8, and the ordered pair 4, 6. So you'll notice in this example, H is a subset of A Cartesian B. That was one of the things we needed. The problem, so property 1 is satisfied actually. So, you know, for an input, does there exist an output? The property 2 is what fails here. Remember, property 2 was the one about like every input can only have one output. And so it looks like as written, 7 was an output of 3 and 8 was an output of 3. We can't have that. So what we have in this last example is H here is a relation from A to B, but not a function from A to B. Okay, so I hope these small-ish examples help. As the examples and non-examples help clarify a little bit what's going on in properties 1 and 2. Now let's go back to examples. I'd like to define, we've used capital A and capital B a lot, so let's use capital X and capital Y. So capital X is the set of all integers. Capital Y, I'm also picking the set of all integers. Yeah, why not? You can, in other words, the domain set and the codomain set could be the same set. And you understand my use of capital X and capital Y is because we often think of little x belonging to capital X. And so, you know, trying to play with your memory of inputs are usually called little x's. That's all. So let's do this to define a function. Now, here's the problem. You notice that I've got to write down, if I do it like in the same format as this arrow here, even though it didn't work, I'd have to describe for you in comma separated form in ordered pair, where the first coordinate should keep going through all of the elements of Z. Unfortunately, there are too many. So writing in a comma separated form is kind of a hopeless endeavor. So I'd like to describe a function to you in one of the other set notations because it'll make it a lot nicer. So I've got ordered pair x comma x squared, x running through capital X. So notice what this is making you do, right? It's like we wouldn't have the time to write things in a comma separated format. So what I'm doing here is you got to now piece together and combine earlier ideas. You got to look at this and go, oh yeah, this is a set. Little g is described as a set, but it's written in that build a set running through another set format, right? So every time you pick an element of capital X, and by the way, capital X was a set of integers, so every time little x is an integer, an ordered pair of the form x comma x squared belongs to the set G. If you want to think about it this way, I don't want you to overdo thinking about graphs of functions, but like if you were to graph this, it'd be like take your standard parabola y equals x squared, but you don't get all those points because the domain is just the set of integers. So like you've got to erase most of the parabola. The points you have, I guess, form the shape of a parabola basically, except they're horizontally separated 1 unit apart from each other, because you only have the points in the graph when the x-coordinate is an integer. Okay, so this is an example, just to put the words to it as I have in the notes. Then, as described here, then g, because you only get one output for each input, right? So when the, so then g is a function from the domain, which you could write, I'll just write the x here, to codomain capital Y, right? So note, just to make sure we're clear about some of these things, the ordered pair 5, 25 is an element of lowercase g. Again, you've got to be working through how to interpret what it means to belong to this set, right? So and the ordered pair -5, 25 is also an element of lowercase g, but the ordered pair pi, pi squared is not an element of g, because you never run through little x being this number pi, which is not an integer. If you write this, at least so I hope that much is clear. And then if you write these two things in more usual notation, we'd be writing g of 5 is equal to 25, and g of -5 is equal to 25. The fact that the same output, 25, is used for two different inputs isn't bothering us. It's not bothering me anyway. What we have is still a function. The fact that, okay, if your inputs are always integers, the fact that, okay, so 25 was an output, but then 24 is not going to be an output because it's not a perfect square for integers. The fact that 24 is an output doesn't bother me. It's not part of the official definition. Right? Not everything in the codomain, let me point to which one's the codomain. Like over here, I've circled it. Not everything in the codomain has to be an output, but everything that's an output has to be in the codomain. I'm going to pause. Maybe I'll keep it here. See if anybody unmutes and has a question. Okay. Then I'd like to address something from an earlier example. Earlier, we just wrote f of x is equal to x squared plus sine of x. And I guess I want to ask, is this a function? And you'll see that this question is kind of problematic, because if you looked at the definition of function, sorry to do this, I'm going to scroll back. Either way you've written it, there's all these quantifiers, for all little a and capital A. Well, what the heck is capital A, right? How are you supposed to check that these properties happen for all elements of capital A if you don't even say what capital A is? So here, I'm going to let you in on, I guess, the sort of secret is that when writing f of x equals x squared plus sine of x, like is written here and I'm currently underlining, I call that a function when I teach calculus or when I teach college algebra. And to be really honest, I am hiding details because they should not be getting those details. What you are finding out, or what I'm about to say right now, is it's totally unclear whether this is a function or not. I don't know. You've got to specify a domain and a codomain. So if I first said that A is a set of all reals, and then I said that B is a set of all reals, and then after having defined capital A and capital B, then said F is a set of ordered pairs of the format x, x squared plus sine of x, as x runs through capital A, now we have a function. So now this is a function from A to B. What I'm trying to get at is the way that we end up talking about functions very often in calculus or in algebra is often we just give the formula and call it end of day, and then just so that I have an excuse of something to help students at that level practice, I ask, especially in algebra, I ask, what's the domain? So that they can practice what it means to based on how the formula for a function looks, they can practice what x values are allowed and what x values are not allowed. Here, you're noticing we're totally flipping around the story. To tell what a function is first, you got to actually, first thing, state the domain. Second thing, state the codomain. These things are stated outright for you. And then the rule is specified in one format or another, whether it is in a formula-like form with like what's circled up at the top of the page, or whether it's given in a set form like I'm underlining right now. That comes third. It comes after I tell you what the domain is. It's totally backwards from how things are done in college algebra, where to create an exercise in college algebra, I give them the formula first and then ask them to compute a domain. It's totally backwards. So you'll notice, in fact, if you go back, look back at your notes for today or rewatch the video or something like that, you'll notice that in all the examples, I stated the domain and codomain first. And so I've got 2 minutes, and I'm going to say that this is a good place to end. It's right where I have written goal in my notes anyway. I don't expect to get as far because of the time delay and announcements and stuff. But the whole point is, in this class, there's not just a moral, but rather an expectation. In this class, and this goes both ways. So saying, and let me just box this from earlier, f of x equals x squared plus sine of x. If I just write that alone, right, this is considered actually unacceptable to fully define a function. Or not even fully, just to define a function. Okay, this is only the rule part, right? So to define a function, you've got to state the domain, state the codomain, and then in one fashion or another, you've got to state the rule. Now that rule might be, let me kind of box them in blue, could be in a formula format like this, or it could be in a set notation. But the thing is, you can't just give the rule alone. So stating the rule is just one of the three parts now, which is really, really different, right? And this goes both ways. So I was experimenting with you to try this here with this example. I say example in quotes. When you define a function for me in homework, you've got to state a domain, codomain, and rule. When I state a function for you, because I either need to as part of the exercise or for a proof on an exam or quiz or in class, whenever I state a function to you, I got to state all three things. This expectation goes both ways. Questions, or we'll call it a day. And just announcement, of course, is exam. Just please, reminder, turn in the exam by the end of the day. And then if you have not already, please start looking at the next homework. Thank you all. Okay, I can stop the recording.